but I actually found math to be more intriguing. I was always interested in the puzzles posed in math. For example, Rubik's Cube, did you know that's just one big math problem? Well, it is. And it wasn't until college that I found out how much math can be used in science, especially in physics. So for me, physics was my perfect match. I got to use math to explain the universe around us, the how and the why of the universe. I was also inspired by physicists coming together from all over the world to help unravel the mysteries of our universe. We are observers of this physical universe. Curiously, we ask questions of nature. What are we made of? Why are we here? What lies beyond Earth? Physics, and in particular particle physics, attempts to address these questions. So we begin with, what are we made of? Zooming in on a living being, we find cells, like tiny factories. How tiny? They're really small. Imagine the thickness of a piece of paper. It's almost nothing, right? But 5 of your body cells would fit lying across the thickness of this piece of paper. That's much smaller than you can see with just human eye. Zooming in even deeper, you know all matter, living or not, is composed of atoms. At this scale, nature obeys quantum physics. That means when we think of a particle like an electron in an atom, we can't say exactly where the particle is or even how fast it's moving. Think about how different this is than your ordinary experience of the world. For example, let's say you're playing catch with a friend. You use what you know about where the particle is and how fast it's moving to know where to run and catch it. But contrast this to the weird quantum world where we don't know that the particle is here or here, and we don't even know that it's not on the other side of the world. Instead, we say that the particle is existing as some kind of cloud, and we can only know the probability of finding the particle somewhere. So our quantum universe is pretty weird, but in some ways, looking at nature this way is a lot simpler than your ordinary description of nature. For example, you could think of 100 different plants and animals right now, the basic building blocks of an ecosystem. Getting even more basic, you can think of 100 elements ranging across the periodic table. Everything that you see around you is made up of some combination of these elements. But still, there's so many of them. In physics, instead, we think about what all these elements have in common. They're just made of protons, neutrons, and electrons. That means everything around you is just simply protons, neutrons, and electrons. Now remember how small the cell was? Just like how you could line up 5 cells across the thickness of a piece of paper, you could line up 100,000 atoms across the thickness of a cell. That's hard to imagine. So I like to think of this analogy, where I think of a tiny little fruit fly compared to the size of a football stadium. That's the size scale between the atom and the cell. So the little tiny fruit fly is like the atom, and the entire football stadium is like a cell. In fact, the nucleus of the atom, where the protons and neutrons are located, is actually really, really tiny compared to the size of the whole atom. This picture is totally not to scale, but if they drew it to scale, you wouldn't be able to see the nucleus because just like the atom in the cell, the nucleus is so small that it's the same as the size scale between the fruit fly and the football stadium. So when you look at the atom, you have this tiny, tiny little nucleus, and the whole atom looks huge compared to it. But if you think about how small an atom is, we can't even come close to seeing one atom compared to the size of a cell, which we also can't even see. So you can imagine how silly it is to say that particles are small. So we've been talking about protons and neutrons. Everything in the world is made up of protons, neutrons, and electrons. However, protons and neutrons are not actually fundamental particles. They can be broken down into smaller units. Those units are called quarks. The type of quarks that make up protons and neutrons are called up quarks and down quarks. But in particle physics, we're not just interested in protons and neutrons as some combination of quarks. Protons and neutrons are just two examples of the many combinations of 6 quarks that exist in nature, which along with electrons and just a few other particles make up everything in the world, everything in the universe that could ever be created, ever has been created. They're all just some combination of these few particles, which is like the physicist's version of the periodic table of the elements that I showed before for chemistry. These set of fundamental particles, along with the rules that govern their interactions, is known as the standard model of particle physics, which describes nature at the smallest of scales. But what is the smallest scale? Is there a limit to how far we can zoom in on the fabric of space and time? We don't yet know. Can we go even deeper? Is there any smaller particles? We're not sure yet, but we think we're getting close. Because at the scales currently being investigated in particle physics, intuitive concepts like the mere difference between something and nothing breaks down. The time and the place in the universe where these small-scale fluctuations were the most important was at the Big Bang, possibly the beginning of time, when we theorized that the entire universe was condensed to an infinite energy density, and the conditions right after the Big Bang determine everything about the way the universe works today, what particles were created, and in what abundances. So, what does this have to do with our world, and how can we test it? Since we're trying to learn about these small-scale fluctuations and the conditions near the Big Bang, particle physics experiments are some of the most energetic places in the universe. We're trying to simulate conditions after the Big Bang, which is the most energetic place in the universe. But that happened a long time ago. We do this by colliding particles into one another, because we want to learn about the rules of the universe, the rules of particle physics. How is it that particle physics obeys this famous energy mass relation, E equals mc squared? We collide particles into one another. We accelerate them close to the speed of light, and at the point of collision, there's so much energy that energy is converted into mass, E equals mc squared. In other words, speed is somehow converted into particles. For example, here's a simulation based on the standard model of particle physics that I was talking about, of 2 protons colliding into one another, just like we saw in the video. This is what was predicted and observed in the discovery of the Higgs boson in 2012 at the Large Hadron Collider. You may have heard of this particle. Its discovery led to the 2013 Nobel Prize in Physics because its discovery was so important in our understanding of theoretical particle physics, and because the Higgs boson represented the last missing piece of the standard model puzzle. At experiments and like those at the Large Hadron Collider where the Higgs boson was detected, huge particle detectors, as big as the size of this building are used to detect that shower of particles that gets created at the collisions. Those tiny, tiny particles are detected with these massive and intricately designed particle detectors. Take a moment to appreciate the scales of these pieces of machinery. Thousands of scientists and engineers come together all over the world. Every week this is going on. These detectors are used to detect these tiny, tiny particles. And look how massive they are. This truck down here looks teeny compared to these ginormous detectors. These detectors, along with the colliders themselves, are some of the greatest works of engineering that humankind has ever completed. And we get to use them to learn about particle physics. So here is a satellite image over Geneva, Switzerland, where the Large Hadron Collider is located. So you can see this yellow line indicating where the collider is located underground. It's so huge. Look at this international airport. The International Geneva Airport looks tiny on the map compared to this particle collider. It's like a subway system underground, just meant for these tiny, tiny protons. The collider itself is an underground vacuum-sealed tube which uses electric and magnetic fields to accelerate two paths of protons, just like you see here. Two paths of protons moving in opposite directions so that when they collide with these particle detectors, creating a massive shower of other particles, all according to the standard model of particle physics. Or maybe beyond the standard model, indicating new physics, giving us hope to explain some of the many unanswered questions that remain in particle physics. So far as we've seen across physics, the universe obeys laws, and those laws appear to be consistent throughout the universe. That means that if there is intelligent life across the cosmos, they're likely studying physics, the same physics that yields life here on Earth. And alongside us, they seek to understand nature, that which transcends life and human experience. Thank you.
Thank you, Kimmy. So we have time for a few questions. And you will get a sticker if you ask a question as well.
Back row here.
Yes.
How come 5 cells equals a piece of paper? Well, 5 cells doesn't necessarily equal a piece of paper, but on average, our human body cells are, like I wrote in the slide, 10 to the minus 5 meters. So that's a length 100th of a millimeter. So that's a size that you can't really imagine so easily because it's so small. So I was just saying that you can see the thickness of a piece of paper. You can't imagine lying anything across the thickness. It would just fall one way or the other. But that's because you're not zooming in far enough. If you're a little tiny little ant, it looks like a little thicker, right? And if you zoom in even farther, then it actually has some thickness. And 5 of your human body cells on average, all of your cells are different sizes, but I was just trying to give an idea of how small cells are, let alone atoms, right? You can't even imagine how small atoms are.
How would intelligent life in other places know what we do here?
That's a good question. Well, I don't necessarily think that they would know what we're doing just as much as we don't know what they're doing. But the idea of science, and especially physics, is that it goes beyond our observations of what we see just happening on Earth. But it's just what's fundamentally true about the way that the universe works. So across the cosmos, there might be aliens, and they also have carbon and hydrogen and electrons and protons, the same building blocks. Because that's what I meant by the building blocks of the universe. And the rules that govern their interactions are the same across the whole universe. So they might be looking in a telescope, facing right toward Earth and looking at our sun. Question over here. Has there been any other particles discovered? That's a really good question too. There hasn't been any particles discovered recently because the more and more we figure out about the way that the standard model works, the harder it is to push forward for more because our theory seems very complete. We know we haven't answered all the questions out there. Like I said, there's lots of open questions, but we've got a very good picture that it's very, everything that happens in these collisions is predictable almost. It was in the 70s and the 60s and the 80s and the 90s that a lot of these particles that I showed for the standard model, that those were being understood. And then that's why we have this theory of the standard model that's so well tested. Years and years of detectors, and we haven't found anything particularly new. So we're at a stage in physics, in particle physics right now, where we have to try something new in order to find, to answer the rest of these questions we have. And that's why there's all these other fields of physics that are coming together to help answer questions in particle physics.
Okay, I think we have to move on, but let's thank Kimmy one more time.